I'm not here to try and sell you anything. As you can see, I'm not a salesman. I'm wearing a short sleeve shirt like Dilbert, and I have a pen in my pocket which tells you that I'm an ex-engineer. What I am going to tell you about today is to give you a very brief introduction to Leonardo, not really to tell you anything in depth about Leonardo's products in this area, but just to try and illustrate some of the features of the space and the range of products and services that people offer. I'm going to touch very briefly on the economic case for autonomy, generally, not to do with defense or security, but I'm going to really think about productivity and what productivity means to society. And then what I'll do is they'll then try and bridge that to the way in which business cases are evaluated in the defense world, because every sector has its own specific features. And then what we'll do is we'll drop down into the sector and think about some of the differences between, say, the market leaders in this area and the people that are trying to catch up. Generically, the difference between the Americans and the Israelis, and, for instance, the Europeans, generally speaking. And we'll then go on and we'll think about some of the drivers, the trends, the enablers that are going to be worked on over the next generation, which will enable the Europeans really to catch up and to serve our needs looking forward. Now, there are some changes that are underway in the world of defense in Europe, which will provide an opportunity, not just for incumbents, but also for people that are looking to move into the defense or the security field. And of course, if you look across the patch, there are some interesting approaches that are being taken. And they're interesting in the sense that they might be copied and put to use more broadly. And then we'll try and wrap up with some conclusions. So, Leonardo. Many of you will not have heard of Leonardo. Leonardo is a relatively new name, but it's actually an old company. If I was to tell you that Leonardo used to be called Finmeccanica, that might not help, because actually Leonardo was a fairly traditional, old-fashioned holding company which used to hold brands. So if I was to tell you that Augusta Westland in helicopters used to be a Finmeccanica company and is now called Leonardo, or Alenia Aermacchi, which does things like regional jets, aerostructures, military aircraft, again, was a Finmeccanica company. It's now Leonardo. Celex, which focuses on defense electronics and small-scale UAVs, well, it's also part of Leonardo. Automelara is a land system, so armored vehicles, artillery pieces. WAS is an underwater systems company, so underwater vehicles, torpedoes, that kind of thing. And we also have other joint venture companies, so we're a shareholder in MBDA, we're a shareholder in Telespazio with Thales on satellite telecommunications, and also with Thales on Thales Alenia Space, which is space payloads. And ATR is a regional jet joint venture with Airbus. So you might not have heard of Leonardo, but you might have heard of some of the products in the past. Now, if we were to think about autonomous systems, and just thinking about one sector, the air sector, and you start to divide that sector up into different segments of the market. At the small end, you've got mini or micro UAS, and they typically are very short duration, and they also have a very small payload capacity. Moving up from that, you've got shorter range UAS, and they tend to have a little bit more endurance or range, and they tend to be able to carry more payload. Again, medium altitude, long endurance space, again, you've got more range and more capacity. So you can actually map each of the participants in the market's offerings onto this sort of mapping in the market. So, for instance, Leonardo's got, at the small scale, we've got the CREX B and the ASIO B, both electrically powered small UAVs. And then moving up in the range, you've got our offerings in the rotary wing space, the Hero and the Solo. And then as you go up in the space, you've got things like the Falco tactical UAVs, which actually extend with larger wings and more capable engines up to the border of the medium altitude space. And then at the very top end, you've got things like the Piaggio Hammerhead and the Sky Y, which are genuine medium altitude, long endurance UAVs. So if you think about the organization of your customer, in the case of the armed forces, like all organizations, it's a pyramid. So at the top of the pyramid, you've got very few customers, and actually at the top of this pyramid of systems, actually you've got very low numbers of systems purchased. But they tend to be higher value because they're more complex. They add more value. At the lower end, the way it maps onto the force structure of the army is that you're actually going to sell more systems, but they'll be of smaller value. Now, understanding how your product actually maps onto the structure of your user community is important as well, because at the lower end, really the reason why you're giving a soldier in the field these sorts of tools is to give them information that's under their control. So really you're wanting something that's small and light and flexible, can be controlled very easily by them, can typically be dismantled and stored away in a backpack, and offers very little of a challenge in terms of its usage, its understanding. As you go up the scale, you tend to result in more complexity, more training needs. So if you think about the electronics that's part of these systems, because if you do a study of the market sector, what you actually find is that about 60% of the economic value of these systems is now wrapped up in the electronics and the software, and actually only about 40% is actually wrapped up in the value of the aircraft or the engines. Generally, what you find is that there's a portion of the system that is in the air, and there's a portion of the system that is in the ground. And actually, from a systems engineering viewpoint, how you partition that is somewhat academic, because these days in modern software tools, modern software methodologies, you can change the partitioning as to whether it's resident on a computer system on the ground or whether it's resident on a computer system in the air. What it really comes down to is how much capacity you've got in your aircraft to accept that computational task, for instance. But the trend, because we're very good at engineering systems to be lighter weight, we're resulting in systems with longer endurance and more payload capacity. The trend, longer term, is for us to produce integrated airborne systems with more of the functionality over time migrating to the air. And there's a number of reasons for why that's a trend. At the beginning, when people were only really putting something like a very simple camera on a UAV, you might have been content simply with getting that camera image relayed back to you on the ground. If you think about it in its most basic sense, the sorts of systems that are at the very low end of the scale in this application area enable somebody on the ground to see further than they can see on their own. So if you go back hundreds of years ago, a regiment might have asked a small boy to climb up a tree and shout down to them to tell them what he could see. Or a little bit later, they might have had somebody who was posted on top of a hill and he was asked to communicate with the rest of the force what he could see. Well, the purpose in surveillance of ever putting anything in the air is to inform somebody on the ground of something that they can't see or can't see very well or understand very well from the ground. Now, as we progress over time, what's happening is that the sensors that you're putting on board all of these platforms are becoming more and more complex. So although you might have been content many years ago of having a simple visual band sensor, now what's happening is that you're getting multiple bands. So you might have infrared being added, or a low light camera. You might have somebody coming along and saying, well, we've now got more capacity. What we'd like to do is we'd like to add a radar so that we can see during the day and the night in all weather. Or you might have somebody that will come along and say, well, what we'd really like to do is to understand what communications are going on the battlefield. We want to know which radio signals are being emitted from which locations. So you might want something like a comms ESM system added. So over time, the trend is for people to get up the ladder of capability and add more and more sensor types that give you a richer set of information as to what's going on the battlefield. And all of that tends to result in there being a higher and higher flow of data from the airborne platform to the ground. And of course, at some point in time, you run into the problem of communications bandwidth problems. And there are some classes of sensor that really do result in that being a fundamental constraint. And it leads to you making the jump and saying, right, what I'm going to do is instead of having a ground station that's acting as my exploitation terminal on the ground, what I'm going to do is I'm going to take that system and move it to the air. And what you end up with is something that's rather like a geospatial information system in the air that's operating in real time, that's operating in a highly automated manner, and it's borderline autonomous. And that becomes a very interesting problem space for engineers that are fascinated by these kinds of problems. So stepping back a little bit, if you think about what the business case is for autonomy, I contend that it's all about productivity. So in the top left-hand corner of this slide, we see long-term productivity growth. And the darker line is the median case. And there are some grayed out lines that are higher and lower in productivity growth rate. But we've got the black case, the medium case is the one that's selected. Now, those lines might represent different countries. So we know that, for instance, Germany is a very high productivity country. So Germany might be a higher slope of line than, say, the UK. UK is notoriously bad at increasing its long-term productivity growth rate. But long-term, it's notoriously difficult to alter the gradient of that graph. It doesn't change very much. You know, it's a really difficult battle for a society to suddenly step up its long-term productivity growth rate. So that's something of a given. It's difficult to change fundamental behaviors in a society. If you look at the bottom left-hand graph, what that's depicting is the long-term debt cycle. The long-term debt cycle runs for perhaps as long as 50, 60, 70 years as a society borrows money to invest in productive capacity. And it's interrupted somewhat inconveniently when we run into something called a deleveraging. And most of us in the room will remember that back in 2007, 8, 9, we went through a once-in-a-lifetime, hopefully, deleveraging as we snapped back and effectively went into recession. Now, The top right-hand diagram is what happens when you take the long-term productivity growth rate and you overlay onto it the long-term debt cycle. And the short-term squiggles on top of that are the normal ebbs and flows of small recessions that happen over time as the economy cycles in and out of growth. Now, I contend that the case for autonomy is to help us to increase the gradient of that long-term productivity growth cycle. And that's important. It's so important that Paul Krugman, who knows a thing or two about these things, he said, productivity isn't everything, but in the long run, it is almost everything. So, and he's a Nobel laureate. So I think that's the case for autonomy. Now, in defense, we've traditionally looked at the autonomous systems as being very suitable for longer duration applications, 24/7 type surveillance applications. Traditionally, anything that was a really hostile or high threat environment, we've wanted to take the human out of that situation because it was such a dangerous place to be. Similarly, when operating conditions are very bad, we want to take the human out. But simply turning up in front of your national MOD and saying, I've got some great technology, it can be long duration, it can go into a hostile environment, and it can deal with harsh operating conditions, doesn't tend to be enough. Because there's a very specific way in which they tend to look at the business case for investment. And if you don't understand the way they break down and analyze investment decisions, well, your business case to them isn't likely to meet with a success. So these dimensions of the problem that they tend to look at, they're called different things in different countries. In the UK, we call them DLODs, Defence Lines of Development. And they break down into things like concepts and doctrine. In other words, how is war conducted? The equipment itself, how much it costs to develop, what the equipment costs are, whether it needs qualification, how easy it is to upgrade, etc. How is new capability to be inserted during its lifetime? Similarly, infrastructure. If you bring something new into your forces, what's also needed to accompany that change to make it productive? Interoperability isn't just a question of interoperability within your own forces, but it's actually about how do coalitions work effectively together. So when you have a coalition of, say, NATO is 28 nations, how do they work effectively? And when they extend their coalition for a particular operation, how do you bring people in? And how do they work together? Logistics, the organization, the personnel and training. All of these things have to be considered in order for you to get to the point of yes with your customer. And typically, new entrants into the defense world won't have the domain knowledge to understand those dimensions, and that's why people typically partner when they want to enter into the defense market. So if we look at the current state-of-the-art worldwide versus Europe in the area of UAVs, really we've reached a situation in Europe where we became dependent upon the USA and Israel for UAVs for a period of time. And basically we imported systems that were battle-proven, which were available off the shelf, and we procured them. And that led to us either buying American systems with the aid of the US State Department's Foreign Military Sales Program, which gave European countries cheap loans in exchange for agreeing to purchase their equipment, or we bought Israeli systems which had indirectly been supported by American military aid to Israel. And what that resulted in was a lack of strategic autonomy in Europe. And strategic autonomy is another kind of autonomy, not the kind of autonomy that we're talking about here today. Strategic autonomy is is your ability to act freely in the world without being held to ransom by anybody else. So if you've got a dependency and somebody else holds that over you, then they can alter your behavior, they can control your behavior. So for instance, if you're dependent on, say, Russian gas, in the case of the Ukraine, well, that's a dependency which they try and use to their advantage over you. And increasingly the case in Europe is that we're trying to minimize the extent that other people have a hold over us and can control our behavior or our views. So the fragmented nature of European defence procurement really came about was because we had all of these individual nations that had their own national ministries of defence and their own budgets and their own forces. And that meant that we didn't aggregate demand in Europe and we didn't coordinate supply. And in turn, that meant that the suppliers in Europe didn't accumulate what I've referred to here as MFHs, which are million flying hours. And that's important because when it comes to de-risking and battle proving, it's the amount of skin in the game that you've experienced. And any process gets better with the amount of volume that you put through that process. And what we're talking about here is predominantly data processes, because such platforms are gathering data on the environment and they are communicating that, usually via a radio link of some kind, to the ground, to a ground exploitation system, and then they're passing it down a chain which we call the processing, exploitation and dissemination chain. And it's when you put many millions of flying hours and many terabytes of data down these processing chains that you get all the bugs out of the system. And that's when you really make a process slick, fast. It needs less and less intervention. But happily for Europe, there are reasons to be cheerful. So in the tactical UAV space, we've got a number of European suppliers that are climbing the capability ladder. Leonardo, one of them, on tactical UAVs, also Thales in France, Techiver in Portugal, Sagem in France, and Airbus in France and Germany. In the rotary wing space, again, there's reasons to be optimistic. So you've got Leonardo, Saab, Airbus DS and Schiebel, who are trying to catch up with the market leader, who's probably Northrop Grumman with their Firescout platform at the moment. In the medium altitude, long endurance space, this is one of the areas where we face the biggest challenge. We've been purchasers of American equipment for many, many years. And we've become a users club of American systems, but that's about to change. I'll tell you a little bit about that. In the high altitude space, really it's really been a story of American domination and European dependence. And in the UCAV space, it's a story of stop-start, of European consortiums starting long-term endeavors and then stopping because of lack of confidence and then trying to regain the momentum later. So this is the sort of system that you've got in the tactical space. The market leaders are the Israeli systems from Elbit, the Hermes 450 and the Textron Shadow. And the systems from Europe, Leonardo, the Falco, the Safran Patroller, and the Techiver Life Ray from Portugal. There are more. And basically what these providers are all trying to do is to get more and more experience with operations, with different classes of sensor combinations, and as they get more capacity on their systems through better engines, better wing design, or bigger wing design, to add sensor combinations and starting to master how you make best use of those sensor modalities and sensor combinations. And actually, probably the interesting thing about this space is probably the merger that's happening between the tactical space and the medium altitude, long endurance space by simply putting bigger, better designed wings and bigger engines onto existing European tactical UAVs, which extends their endurance and payload capacity up to the borderline of the American systems. In the rotary wing space, again, it's a story of American leadership. But what's happening is that Europeans are coming along who have been designers of helicopter systems in the past, and they're now adapting those helicopters for autonomous use. So a good example here, the Leonardo Solo system, which is actually from our facility in Poland, which used to be a company called PZL, if you know that. The Saab Skeldar system, which is now a joint venture with a Swiss company called UMS, and Schiebel in Austria, and in France there's the Airbus VSR 700, which is a development program at the moment. In the American space, well, the market leader for many years has been the General Atomics Reaper/Predator series. And what's happening now in Europe is that the French, the Germans, the Italians, and the Spanish are clubbing together, not just to be users of American systems, but actually to design their own system themselves. And this is a really important development because it's this middle space in the market where you've got it's a combination of relatively high volumes of units of systems and the higher complexity of system, which leads to the multiple of units times dollars. So it gets you the revenue levels that you need to sustain and grow a business significantly. So there's a program within Europe at the moment that's at the definition stage called Euromail, and that's going to result in a system design midway through 2018, which will then go through a gating process, hopefully that will lead to a European-sourced system. And potentially this is a major opportunity for the European supply chain. As much as anything for the data that comes off of these systems and then goes down through the ground exploitation system and down the processing, exploitation, and dissemination chain to be turned into intelligence product. And if you think about the number of people that are involved in the process, there might only be one person in the control room that's piloting the system, and another person in the control system that's managing the sensors. But there might be 20 people in the chain who are processing the information that comes off it and turn it into something that can be used by the military intelligence teams. So if you think about someone studying aerial photographs, well, there are still people studying aerial photographs. More typically these days, there's people studying video streams. And what's happening is that these tasks are being automated. So you've got someone who is being supported by a computer network and tools that sit on those computer systems on that network. And then those tools are incorporated into a workflow, and then the workflow is then automated. So it's got some parallels with the world of process-based automation, even in companies like insurance companies, for instance, where you're processing documents. We're talking about terabytes of information that's coming off of these platforms every day that needs to be processed. In the high altitude space, you've got, again, a story of American dominance with Global Hawk. There has been efforts in the past to get the Europeans to do things together. For instance, through the auspices of NATO, there was the NATO AGS system where we had an allied ground surveillance ground station that was built by the Europeans, and that is due to come into operation soon. Germany tried on its own to go ahead with the Eurohawk, but then ran into the problems of a major bill in the region of 600 million euros to try and qualify that system for operation in a civilian airspace, and they ended up deciding to go no further. And it's possible that Germany might decide at some point to go ahead with the maritime version of Global Hawk, the Triton. But it's also possible that there might be a major rethink in that plan, because we're getting towards the sort of time frame where NATO as a whole will be considering how it replaces the AWACS system. And it's entirely possible that that system turns from a centralized system of one platform with sensors on it to being a dispersed system of many platforms and many sensors that are all networked. So that's an opportunity longer term. UCAVs, again, a story of American leadership. There has been various efforts in the past. For instance, the diagram at the bottom right is the Neuron team of a broad selection of European countries led by France. That program got to the stage of a flying demonstrator, and then just as they had to commit to larger scale funding to go forward into production, they wanted to stop. So what's happened is that the British and the French have gone on together, but even here they're not actually working on an identical end design. They're actually cooperating on the class of problems. So the sorts of drivers, trends, and enablers, well, from a user's perspective, the big change is really asymmetric warfare, and what that results in is the need for persistence, and in some cases, extreme persistence. And it's this need to look everywhere all of the time which is driving our approaches to platform design and the sorts of sensors that you put on board. And really what it's doing is it's making the data volumes explode. And what's happened over the last few years is that in this processing, exploitation, and dissemination chain, what we're now doing is we're defining standards for the data sets and for the data interfaces. And what that's going to do is to then allow people to standardize the tools that will use to process the data and to, in a sense, automate the tasks. Also, the problem that we've got is looking for very difficult targets 24/7 within a comms bandwidth constrained environment. And what that's really doing is it's resulting in a move from the processing from being predominantly on the ground to moving up towards the air. And if I was a young 20-something engineer and I had the first 30 years of my career ahead of me rather than the past of me, that would be the area I would choose to work on, because I think that's a fascinating area. And the area of operator workload for the piloting of the vehicle and for the control and management of the sensors themselves, that's largely been automated. So what people have done is they've broken down the tasks that people have in the past had to perform manually, and generally those tasks have now been automated, and they've been grouped together into macros. So you've got a series of macros that are available to you now, which really means that the operators are simply supervising the computer systems which are running the show. Really that means that you're looking for confirmation. So if I was surveying this room and I was looking for objects of interest, for instance, Charles, because I know Charles's name from a presenter earlier, I might identify Charles as an object, but simply, equally well, Atlee might be an object. Now, how do I decide in a computer system whether Atlee represents more of a threat to me than Charles? Well, Atlee is wearing a tie, and he's from Norway. Well, I know he's from Norway. And Charles, well, Charles isn't wearing a tie, and he's got a beard. Does that mean that Charles is more of a threat? Well, that's cognition bias. And one of the advantages, of course, is that computers can be less prone to cognition bias than humans, and they're more objective about these things. But it also means that you run into the limits of what your computers and your algorithms can do. So every now and then, your system might flag up an object of interest in the scene, And you've got to decide as an operator whether he's somebody that you want to follow more intently to determine their intent. And that's the area now that we're getting into. Difficult challenges to determine who is a true object of interest. And longer term, well, in the area of UCAV, well, you're talking about whole platform autonomy. And when I speak about whole platform autonomy, I'm not talking about weapon systems that are autonomously let loose to do whatever they want. There's always a human in the loop controlling a weapon system. A weapon system is never something that is automated or autonomous. But the UCAV space is one, because it's far away in time, actually it's a great example of how by setting a long-term goal that's far, far away, you can actually get a group of people to rally along a long-term vision that acts as a technology driver that brings people together and unites them in a common goal, where otherwise they might be competing against each other in the same market segment. So it's a useful thing. The other area really that's useful to look at is what the market leaders are doing. So if you look at what the Americans are up to, because the Americans are always very good because they tend to put things into the public domain because of their system of government. The Americans have got something called the third offset strategy, and that's basically their long-term technology plan for defense and security, in broad terms. So the first offset strategy was about nuclear superiority and how you take atomic weapons and miniaturize them. Second offset strategy was really about precision-guided weapons and the sensors that you need to make them effective. The third offset strategy, if you look at it, you think, wow, this is exactly the tasks for R&T that pretty much industry across all sectors needs. Deep learning systems, human-machine collaboration, human-to-machine combat teaming, how we work effectively together, assisted human operations, exoskeletons, things like that, and cyber. Pretty much what any sector of the economy is looking at. So I think you're going to see the degree of complementarity between defense and civilian applications increase, and you're going to see far more civil spin into defense than you've perhaps seen before. Now, one of the significant opportunities that exists for people that want to get involved in defense is that for the first time ever, Europe has decided that we need to have something called a defense action plan. And within that defense action plan, there's going to be, for the first time ever, a European defense R&T program. And that's being briefed today in Brussels to the public. And it's being sized at the level of 500 million euros per annum. So 3.5 billion euros in the next multi-annual financial framework. And what we're about to go through over the next 3 years is the pipe cleaning process, the preparatory action, to give the participants a chance to get to know this space and how it works together and the mechanisms that are going to be used. So that's going to be a 3-year preparatory action sized at the level of about 90 million euros, budget permitting. And it will prepare the way for something called the European Defence R&T Programme, EDRP. And within the PADR, there's a technology demonstrator. And surprise, surprise, it's focusing on autonomous systems, in this case in a maritime surveillance environment. So, if we have a situation where, rather like Horizon 2020, we have a defence programme in Europe, it asks some interesting questions. So, for instance, when Europe sits down together and tries to work out its common goals and its common priorities, it's going to end up defining the capabilities that it needs for itself And that will, in turn, drive the research priorities. And that's not been done before in Europe. We've got a situation where in Europe there's already 700 million euros that is scheduled to be spent on the robotics area through the contractual PPP, EU robotics. Well, if you're going to have a defence programme underway in 2021, one of the questions will be how do you coordinate between the defence world and the civilian world? If you've got a civilian world where they're actually working on open source efforts like ROS Industrial, well, it asks you the question, will there be a ROS military? Or in the airborne world, if you've got drone code, will there be a military equivalent? Who knows? Anyway, I'll move on. I'm getting flagged. There are some interesting models for adoption. People generally are moving away from the traditional approach to R&T, where you have a linear progress from the left-hand side of the page to the right-hand side of the page. And what they're moving towards is a grand challenge-based approach. And there are some good examples of that at the moment. For instance, in the UK, we've got, in the defence world, we've got Unmanned Warrior, which is a program that takes place every 6 months. And it brings together, at the last count, something like 40 unmanned systems. Autonomous last mile resupply is, if you like Amazon drones being applied to the defence world. And I'm being cut off by our moderators, so I will leave it there.
Thank you.